Um, Thank you very much for having me, and it's great to see friendly faces. In fact, my old collaborators, Al and Johannes and Tom in the audience. So I hope I would do them justice. Also, I looked at the name of this seminar. It's called just very boringly the online machine learning seminar. Al is very good at coming up with acronyms. I'm surprised he hasn't come up with a good acronym for this. So I'm just going to call this the online learning seminar Kasperjik de Biase for now. So thanks for having me. So I think this is going to be a mostly a mathematical audience, and I'm coming from sort of a mathematical physics background. So I'm just going to give a little bit of an overview about why I got into this whole field of machine learning, and completely as an outsider, and why the mathematical physics community is very much interested in this direction. So I don't think I need to emphasize too much that algebraic and differential geometry and topology and representation theory in any combinations of these words is really the right language of physics. So this is a very important message that's been carried on for the last I guess almost 100 years. When you think about what gravity is, gravity should be thought of as Ricci two-form on tangent bundles and so on. And what is an elementary particle? It's some irreducible representation of the Lorentz group and so on and so forth. So, for example, string theory, for whatever string theory is really just a brainchild of this gauge gravity geometrization tradition. So everything on the left is some observable in physics, and everything on the right is something that an algebraic geometer or topologist can appreciate. But so this has been going on since at least Einstein. But there has been a fundamental shift in the last, I would say, 10 to 20 years, because there's been a new exciting era. Because these things that I guess this community is more familiar with, things like SAGE and M2 and GAP and LMMDB and GRDB, all of these things have now become to be indispensable tools for physicists. This has just only happened in the last 10 years. So if you ask a theoretical physicist whether the person has heard of Ricci two forms of tangent bundles, that back in the beginning, mid 20th century, people would have known that. But the fact that a theoretical physicist even heard what a SAGE is or what a LFMDB is, that's really on the last 5 to 10 years. And that's been a conceptual change really for the community. And I've been, very happy in just trying to push for this direction for physicists to appreciate these things. So just a one-liner of what string theory is and why this inspired at least myself and my group in doing this kind of stuff is this indisputable equation in string theory that 10 is equal to 4 plus 3 times 2. This is probably the only equation in string theory that everybody agrees with. And it's just the fact that this string theory is a theory in 10 dimensions, is a theory of quantum gravity in 10 dimensions. That's not a problem. So it is a unified theory of quantum gravity in 10 dimensions. And the problem is, there are 11 dimensional versions of this, but let's not go there. But the point is that we don't. Our observable universe is without a doubt 4-dimensional on a macroscopic scale. It's 3 dimensions of space and 1 dimension of time. So there's somehow you need to compactify away the extra 6 dimensions. And the standard solution is to take the extra 6-dimensional manifolds as some kind of a 3-dimensional complex manifold. The complex structure is needed in order to allow chiral representations for fermions. So that's one of the basic reasons why we need a complex manifold. And in fact, the traditional solution, and that really goes back to the mid 80s to early 90s, is to take this extra complex manifold, not only be complex but also Kähler and Ricci flat. In other words, to take this as a Clavier. And I want to emphasize, of course, this is the standard solution that's been going around for about 20-30 years. We now realize that there are many more solutions, that the landscape of possible solutions is much bigger than the Clavier landscape. So there are things like G2 manifolds or Claviers with fluxes and so on and so forth. There are various other solutions, but the traditional solution is to take this as a Clavier manifold. Oh, this is kind of nice. Once you have the geometry of this complex geometry, this is kind of is very beautiful in this sense, is that the algebraic geometry, the algebraic topology of this manifold completely determines the physics of this, our four-dimensional universe. This is a very nice way of thinking about physics in some sense. In a way, it gives the geometrical explanation of why the universe is the way it is. So, for example, there are three generations of fermions and fundamental fermions in our universe. The standard model comes with that. There's no extrinsic explanation to why. Why is it that the electron comes in pairs with a tau and so on? Why do neutrinos? Why is there extra structure in what we observe? So one good thing about string theory is that at least from a point of view can translate that problem to saying that is because of certain topological properties of this internal space. So this is a very nice to Kepler's old answer. Of course, it doesn't. So you've switched one very hard problem for another very hard problem, which is, yes, you can explain this all of the properties of our four-dimensional universe in a geometrical way, but how do you select this geometry? And that we don't have an answer. So that's called the vacuum degeneracy problem. The problem is that there's so many ways to select, even within, I'm going to show you some examples in a minute, of finding, say, Kähler manifolds in complex dimension 3, that is just extremely difficult to have a good selection of why you should choose particular manifolds or particular bundles of particular manifolds. So there are various philosophical reasons you want to take, or maybe it's because our universities. So all of the traditional philosophical problems in physics now become philosophical problems in mathematics, right? So the universe is the way that it is because maybe it's anthropic. That changes the problem is that, well, there is a particularly anthropically chosen manifold. Is that true? We don't know. I'm tending to, I think this is because I had always been under huge influence of Philip Candelas, and so he really fundamentally believes there should be a geometrical selection rule which determines the properties of the universe. That's just kind of nice. So as I mentioned, so this is the vacuum degeneracy problem, and it is still the biggest theoretical challenge to the string theory. And this is probably the reason that string theory has received so much criticism, is because this has so many choices that we've essentially switched from one hard problem, the problem of quantum gravity, to another very hard problem, which is how do you find particular manifolds in the space of manifolds? To me, that's a much more interesting problem because it involves much more beautiful mathematics. I mean, it's an interesting problem anyway. Like, what is the generic feature of the space of, say, smooth compact Labial manifolds in various dimensions? Or what is the metric on the moduli space of Labial manifolds, and how does that metric on that moduli space affect on the metric on possible selections of the landscape? So the people really were thinking about this back in the 2000s. Like Mike Douglas wrote this beautiful paper on the statistics of stream vacua, which is essentially really a way of doing statistics on the space of manifolds and their algebraic cycles. So what is the distribution of such things like? So I think this is one of the very first papers that to even think about algebraic geometry in such a way. And then papers like this in the same year of so-called KKLLT paper, when they realized this is the number that got into the public domain, 10 to the 500. And this is the number that received so much criticism. It's because, so this is the reason they got this number to be so big is that they basically did a back of the envelope estimate. They took the number of known Labial manifolds, and they took the number of possible algebraic cycles on these manifolds, and it's roughly estimated to be something like this. But today, the situation has gotten worse rather than better in terms of just allowable solutions to possible things like our universe. It's gotten F theory, which is another version of string theory, gives numbers as big as this, right? And of course, I want to emphasize, if you take the space of manifolds that look like this and you just randomly compactify it, you will not get anything like our universe. Right? You're going to get something like 17,000 generations of protons and like 5 million Higgs particles, which is just not what we observe. So it is very, very rare that you do hit something like our universe. The current estimate in physics is about 1 in 10 to the 10. If you just scan through this, that vaguely, remotely looks like our observable universe from the space of random compactification. So it's, of course, these numbers are very much estimates rather than any theoretical basis. And of course, for this community of mathematicians interested in what we do, the fundamental reason why we get numbers this big is just because, algebraic geometry tends to lead to combinatorial geometry. And once you're in combinatorial geometry, you're really in exponential and multiply, doubly exponential growth range. So, for example, to give an example that Al, for example, has been and Gavin Brown and friends have been very much experts in this area, which is this very beautiful problem. So this is since I think not everyone here is an algebraic geometer, so I'll spend just a few minutes explaining this beautiful database. So if you look at this problem of combinatorial geometry, so look at the reflexive polyhedra in n dimensions, right? So this is a very nice problem. These are integer polytopes in dimension n, which are reflexive in the sense they have a single interior lattice point, which you can take to be the origin, and such that all of the bounding facets are at lattice distance 1 from this interior point. So you can check that this is true. And it's a theorem that these things are finite in every dimension up to SLNZ. So you can classify these things. So if you do in dimension 2, it's known to the Italians in the 19th century that there are exactly 16 of these. So these are called the Fano polygons. They're very, very nice ones. And in dimension 3, it was already unknown until I will mention this in a minute, until almost the year 2000. So why would algebraic geometers be interested in this? Well, it's because if you take any of these polytopes, this lattice polytopes, you can construct a toric variety out of it. And this is not a necessarily smooth toric variety, but then this toric variety, if you take the anti-canonical hypersurface in such a toric variety, there's a beautiful theorem of Borisov and Batirev, which says that this is a Clabia hypersurface. You can choose the Clabia to be sufficiently generic, the hypersurface to be generically generic, that this Clabia will be smooth even. So if you take the hypersurface in the toric variety of this 16 Fano polygons, the toric varieties for these, you get 16 very beautiful elliptic curves. So that's Clabia one-fold. So people have studied this, the very beautiful geometrical number theoretic properties of these 16 elliptic curves. And of course, from physicists, this is just the baby case. The torus is just the baby case. We really want to go to dimension much, much higher. So then they were confronted with this problem. The 16 were up to the 1890s, but then there was just no data point even for the next one. And so Kreutz and Skarka did this really impressive work at the turn of the century, in 1999 to 2000, where they just started to actually sit down with a Pentium machine and to find all possible such things up to SL2Z and SL3Z. So in dimension 2, in dimension 3, so now you think about these are reflexive polyhedra, and then there are three-dimensional Fano varieties, or Gorenstein Fano varieties, as I think Al likes to call them. Then you take the hypersurface in those, they're K3 surfaces. And they turn out to be 4,139. And the next one is the dimension 4 one, which is this Gorenstein Fano toric varieties in dimension 4, and you take some generic hypersurface in that, and that will be a Clabia threefold. And that's the one that I mentioned here, which forms a part. That's just a part of solutions of possible Clabia threefold. And that number is huge, right? It's 500 million. And it's quite impressive that you can actually do this by turn of the century technology. And they were doing this, the running time was something on the order of a year, and they ran it, and it took, whatever it is. And the next number is already open. Nobody knows what the next number in the sequence is. You can type this in OEIS, and there's no prediction. It's too the data set's too small to predict what the next number is, but it's expected to be, I think this is a double exponential growth, or at least a single exponential growth. So they're huge to a number of things. So there's some preliminary things that we've been doing with physicists to triangulate this data, to do the actual physics with this kind of stuff. But this is a perfect illustration of why we end up with such huge vacuum degeneracy problems in string theory, because once you're in the land of combinatorial geometry, you are in there's nothing that'll stop this kind of crazy growth. So, but of course, you take this kind of data, this kind of numbers, well, forget about this kind of numbers. You take some things like 500 million to data scientists. They're like, well, this is tiny. We're not afraid of this. So, so back in 2017, myself and also some of the independent groups were thinking about, well, let's just, is it possible to machine learn, not necessarily this set, but this is still very much an ongoing program of just to see, what can modern data science say about this data set? And indeed, what I would say, just basic generic problems in the string landscape. What can you do with the powers of modern machine learning? And I think Al just had a recent nice paper, I think last year, with friends, I think Coates maybe, and maybe Johannes is on that too, on just machine learning this database of GRDB, the funnel polytopes on GRDB. That's really nice recent work. So, which is kind of nice, in 2017. So this kickstarted a new series of conferences in the string community called string_data. See, I like the underscore is very crucial. It's the only conference that has an underscore in it. At least in the physics in the math physics community, the underscore is very nice. It happens to be the year that Sophia from Hanson Robotics got citizenship from some Saudi Arabia. So it's 2017 is a good year, and that's also the year when my son's born. So for me, it's a very memorable year. So, and it got me thinking of that. The fundamental problem of what we're actually doing is the following claim. Now, I've said this in front of algebraic geometers, and I haven't been shot, so it's okay. I'm become an extremist in saying that algebraic geometry is an image processing problem. And of course, this is a very vague statement in the sense that, if you take any typical computation in algebraic geometry, so I'm not even going to bother explaining what this manifold is. This is some multiple complete intersection in products of weighted projective space. Okay, fine. You keep some degree information, and a typical computation in algebraic geometry and consequently in string theory and mathematical physics is to compute topological invariance of these things. And we know what to do. Bourbaki tells us, just chase Euler sequences. I've been doing this all my life, and a lot of this is implemented in Macaulay too. And it's all fine. But of course, there's only so much you can do because Grosvenor base is extremely difficult, and that really is a double exponential complexity problem. So people have computed now, people in the community, things like this. But you take one of these things and you can compute that, for example, the Hodge number H21 is 22. So what got me thinking in back then was that, well, how is this any different from the image recognition problem that this digit in this picture should be associated with the number 22? And so I at the time, because I was very much a novice to this machine learning community. I still very much not an expert in that, but it's fun. You see, but you try it. And I didn't expect it to work at all. But then the surprising thing is, if you take images like this that represent these matrices or appropriate tensors, basically problems in algebraic geometry you can find a good tensor representation, and then any computation, whether it's topological invariant or bundleable homology or whatever it is then a labeling problem of images of such a type. and then you train, you do a standard machine learning thing and see how far you can go, right? At some level, you think that this is going to well, at the time, I didn't even know about this theorem. So at the time, I didn't even know about these universal approximation theorems. But at some level, you would expect what we are doing is, universal approximation theorems for neural networks is essentially a very, very fancy Taylor expansion. It's not analytic, but it's a very highly generalized Taylor expansion. And because Taylor expansion can smoothly approximate any smooth function, the universal approximation theorem just says that, given sufficiently complicated neural network, you can approximate any function essentially. And because algebraic geometry, this problem here is a very, a very non-smooth piecewise linear function of some variety. You would expect there might be a sufficiently complicated neural network that approximate this. So does it work? The short answer is yes. And I did with some very simple cases, but now this is people like Harold Erban and Finatello. They've done some very serious work on the latest convolutional networks, and they can get precision in the 99.9 range for just predicting topological numbers when you train something like 80% of in certain databases and trying to extrapolate validating on the test set of 20%. So this is very nice because algebraic geometry is very, very much structured, which is kind of nice. So this got me thinking. So I'm going to be now a little more speculative on is it possible to now we're way out of thinking about problems in algebraic geometry or in string theory. But what type of problems in mathematics are amenable to this kind of analysis, right? So this is at least some kind of a speculative idea. So I'm going to give you a couple of examples for fun. So here's one. So I'm going to give you this one. So okay, it's hard to make this interactive online, but I'll give you this sequence, and you can probably tell me what the next number is. Right, I think no one needs to raise hands or anything, but I think you can pretty much see. Yeah, I can. So this is divisible by 3. This one is a bit harder. By the way, feel free to shout out anytime. I mean, generally, if you have questions, comments, criticisms, so please just interrupt me or raise your hands or whatever. So this one is a bit harder. So to cut, so I'm trying to, in looking for my chat, the meeting chat, I have now covered up my progress. Yeah, here we go. So this one turns out to be the sequence of odd integers and labeling what is prime and odd. Right. The next one is hard. Right. Now, it really is hard. I think you have to be very, very inspired. You have to be a John Mackay to, in order to just look at this and say, "Oh, I know what this sequence is." So this sequence is the parity of the number of prime factors. So it's the Liouville lambda function. So the question is, humans didn't struggle with this. This one, after a little bit of guess, you might get it. This one is very, very hard. Is it true that for generic machine learning algorithms that they will struggle with the same level of struggleness, if that's a word, of the human eye? And this can be really, in a way, quantified. So let's give a good representation. So sequence prediction is very difficult. So let's do some feature engineering. So you can take these are all binary sequences, right? So what you can do is, for example, you can take a sliding window of length, say 100 or 1,000, whatever you prefer, and you try to predict the next one outside of this window. Right? So for example, this prime sequence, you take the first 100 of this and you predict 101, then you slide this 1 and you go from 2 to 102 to predict the 103rd prime, and so third odd integer, prime or odd. So, and then you have limitless data, right? So you can easily generate millions of these kind of labeled binary. It's a binary classification on a binary vector, right? And then you can pass it to your standard classifiers. So this is the kind of thing that I really enjoy doing with Tom Oliver, I think, is in the audience with me, he is actually a card-carrying number theorist. So the great thing about the great fun thing about doing machine learning is you get to meet friends in all different communities, right? So I meet Al and Johannes in the algebraic geometry community. I meet Tom in the number theory community, and it's just like you just keep on. I feel like a peddler, and you're selling some kind of shoes or something, and you can make new friends, which is always very enjoyable. So then you say you pass this kind of binary classifier, and you throw an SVM, as a support vector machine. Sorry, this is an MDUP. This is supposed to SVM. Base classifiers, whatever. Take your kitchen sink, your grandmother's favorite neural network, whatever, and see how they behave to this classifier problem. So as you would expect, kind of interesting, the Mod 3 problem came out immediately. If you try with any of these things, it immediately comes up with 100% accuracy with 100%. So I'm recording I'm recording the naive precision, that's the percentage agreement, and the chi-square. So that's just as a separate check that getting nonsense. So that's great. So your machine can learn divisibility in this sense very, very quickly with no struggle, just like the human eye would. The prime Q problem, so here you need to balance that a little bit because the primes get rarer and rarer. So I did a bit of a squishing up to x over log x, and it's not random. It's learning something. I don't know what it exactly is learning. So maybe someone has some insight as to why is this not like completely random? Like in the case of the Liouville lambda function, if you try this sequence in any kind of feature engineering that I've tried, you will get nothing more than 50% precision and 0.00 something like chi-square, which means that your confusion matrix is completely random. Like that you might as well just toss a coin. And this apparently is a big problem because I think this is one of Peter Sarnak's challenges. Peter Sarnak says, this is a really, really random function. And if you can predict anything in it, then I think he'll give you money or something. So somebody asked a question. So is binary classification learning robust? So I mean, well, I guess in the sense that the Mod 3 one is really 100% correct. There are no outliers at all. And then these percentages are they are what they are. At least. I mean, with the Mod 3 problem, I think it's because it's actually it's a linear regression problem, and it's really completely found that there's no outlier in this problem in this multiple 3. These ones, I like someone to explain to me why is this doing a bit better than 50%. I have no idea why, but it's kind of, I'm hoping that it's doing some kind of a sieve method. But it feels as if that's almost too sophisticated for some generic learning algorithm. So it's learning something, but it can't be doing sieves because it seems a bit too much. But yeah, so does that answer the question?
Yes. What I'm trying to get at is that learning patterns, which is what the neural networks seem to be doing, does not imply learning because the phenomena could be deceiving because you don't know what's going on underneath. So it's learning the surface. But that's why I hit the issue of robustness, and that's I think it's a bigger problem in artificial intelligence and machine learning, which I don't think if anybody has some more profound understanding. That's why I asked if we know anything about how the machine learns.
Yeah, that's a very good question. I don't know. And in fact, I'll get to a little more about this later. I think one of the biggest and most important challenges for mathematics is to know what that robustness is. Because if you can start predicting a function which is actually doing this, I mean, it could be a complicated function, but at least it's completely robust and completely correct, then this goes really under a new way of doing conjecture formulation. And that would be really, really, really nice. And I will mention a work that the DeepMind paper, probably you guys all have heard about, which did this shortly. And there they did achieve this robustness, which is very nice. So I will mention that in a minute. So but for me, since I'm just having fun and I'm making friends, so which is great. So a big thank you for my fantastic students, especially JK, Ellie, and Ed. They've been doing a lot of, we've just been basically mapping not just the landscape of string theory, but basically the landscape of mathematics in whatever way we can. So, physics, algebraic geometry, number theory, whatever representation, combinatorics, you name it. I think Al's names should be there somewhere. If not, I apologize. Al and Johannes' name. Yeah, there we go. So I didn't. Yeah, I'm good. I'm good at remembering my friends, which is more challenging. So we've been doing these papers with this in about a few years. You're beginning to forget all your collaborators, and then you offend and they don't become your friends anymore. But I think I have all their names. So thank you very much for exploring this with me. So this now becomes a little more speculative, and I think this, in some sense, it partially addresses at least Yanis's concern, which is it's got me, I don't know, it gets me thinking, like, how does one actually do mathematics? What are we doing? The one way to do it is go back to Russell and Whitehead, right? So they really started this Principia Mathematica program. Of course, it really should go back to Leibniz and Frege if you really go all the way back to the German school, to axiomatic, to axiomatize mathematics line by line. Of course, this program was really killed by Gödel and Turing and Church, right, because of incompleteness theorems. But this didn't stop mathematicians to continue with the ATP programs, the automated theorem proving program. Just because they're unprovable theorems doesn't mean that the vast majority of statements in mathematics can be proved. So let's see how much we do. So this is a quote from my dear friend Min Young Kim, who's a very, very insightful mathematician. He says, which just greatly summarizes the point. And unless you're a very, very sick logician who thinks about way out there, in centers numbered 3 trillion, that's not provable. Most theorems can be proven in mathematics, and statistically, and those are the ones we're after right now. So there's been a long story to this. I will partially I won't bore you with the details, but partially because I really don't know this program very well. All I do know is that Kevin Buzzard and friends, yeah, good point. Yeah, exactly. That's a good point from Yanis as well. Killed in the sense that people don't do Principia Mathematica in the Russell Whitehead sense anymore. Yeah, absolutely. But that's exactly right. So this is partially why the ATP program, which is very, very much thriving, and Kevin Buzzard is one of the torchbearers for this thing with the so-called Lean. I played around with Lean a little bit, and it's a wonderful, wonderful software where they to my knowledge, they've collated hundreds and thousands of intermediate steps of proofs of all levels of undergraduate mathematics. I think they have completed this bit in the sense that anything you are likely to be taught as an undergraduate, well, unless you're Russian, then you have a different, bigger set of mathematics you've learned. But at least to the standard undergraduate program at Imperial, they have put all the proofs and the intermediate steps into Lean, and they can check. And they checked it, I think, a couple of years ago, and undergraduate mathematics is self-consistent, which is great. So far, they haven't found an error. So like Cauchy, residue, that's all good. Weierstrass is all good. But this is not a joke in the sense that Buzzard has found just simply wrong papers published in major journals. And so mathematics has gotten to the point where, the subtle things can escape the referee. But anyhow, so this is exactly what I'm not talking about here, but I just want to mention, and I want to call this kind of thing, top-down, bottom-up mathematics. We're trying to build mathematics from the bottom, in the sense of Gödel. The kind of stuff, what we're trying to do here in this exploration with all my friends is trying to see how to gain intuition in mathematics, which in some sense, I think is really how mathematics has always been done anyway, right? We write our papers backwards. We doodle, we experiment, and then we write in a very formalized way. And so, and I call this I like to call this like more of a top-down mathematics. It's intuitionist mathematics. I know there's this huge debate between Hilbert and Brouwer between formalism and intuitionism. So this is kind of nice that this is coming back. So in some sense, the ATP program is the formalistic approach to mathematics in the sense of Hilbert. And the top-down approach is Brouwer's intuitionistic approach to mathematics. And this intuitionist approach to mathematics, this top-down approach to mathematics, is really what I think machine learning is extremely good at. So, for example, I think you guys, maybe I think Al has heard this joke before, but I like to say this joke for people who haven't heard it. What is the best neural network of the 19th century? Well, it's the brain of Gauss, right? And undisputed. That is by far the best neural network that the 19th century has ever seen. And so, because he can look at this and say, well, this is clearly x over log x. And this is exactly, I use this example is because in some sense, I think we are at the stage, we're just beginning to be at the stage where we can improve on the brain of Gauss in the sense of, in the sense that we have very, very large and complex neural networks and the like thereof in machine learning. And how do we look at graphs like, the days of just looking at a graph and making a major conjecture in mathematics is over. I mean, it's just not possible. Any major, if you can just look at a graph and just know exactly what it is and plot it in a two-dimensional plot, I think it's just not possible anymore. But if you can get more sophisticated data and ask machine learning to help you to raise a conjecture, then that is very much where we are today. And I think we're just beginning to touch the surface of this. So just to give a couple of examples, so this one I really enjoy doing with Mignon, which is to take, say for the first question is, every Latin square is, every Cayley multiplication table of a finite group is a Latin square, but not vice versa. So Latin square is just a Sudoku. So is it possible to distinguish the the proper finite groups from the space of random Latin squares? And now there is a theorem that does the trick. And that's a robust theorem. You can check. There's this called the quadrangle theorem. Basically, you have to check in the Latin square. You have to check associativity, which is not built into Latin squares, but must be built into Cayley tables. And so, but if you throw in a couple of 100,000 of these and just mix it all up, this all defined up to permutation anyway, so you can feature engineer that into a vast space. And you can just ask so for example, a base classifier to do this, and it does it fairly well. It's not completely great, but okay, but it's nice. So this structure is kind of nice in terms of being recognized by your generic ML. A much more interesting problem, and this one I really like people to tell me more about, which is so what we did was something more more basic, which is to take the space of Cayley multiplication tables of the say first 1,000 groups, finite groups, and label all the simple ones. Now I know there are not many simple ones in that set. They're vastly over-dominated by the non-simple ones. So you need to feature engineer by enhancing the permutations on those. And now you can generate a Euclidean space of dimension n squared up to the n, n, where n is the last order of the group that you've used. And then you just plot it in this n squared space and use a support vector machine. Is it possible that does this even, you can distinguish the simple groups from non-simple groups? And to our surprise, it's doing the support vector machine can give this level of confidence. Now there is no theorem of such a type in representation theory that you can even just plot the groups. So this is a proto-conjecture in the sense that the simple groups and the non-simple groups are actually separated. Why should that be true, or even what theorem to use to prove that? We don't have the technology to do that yet, but it would be very nice to do this. So just to reassure us, this is not a random accident of all this, this sporadic distribution of simple, no puns intended, sporadic distribution of the simple ones. We tried to, so we used Cayley table, and this is working in progress with Jijala and Mishra, which is, let's take another representation of finite groups, right? So every finite group is a subgroup of some permutation group Sn, Sk for some sufficiently large k. And in fact, all simple groups are two generated groups. This is a kind of amazing theorem from representation theory that, even the monster, it only takes two generators, two matrices, that's it. And you just, so now we have another way to do it, which is you take the space of two random matrices from permutation matrices, so ones and zeros, binary matrices, and you just generate them. And if they generate a simple group, you mark it as 1. If they generate a random non-simple group, you mark it as 0. So this can make you go much, much higher. So we've gone up to S8. So that's 8 factorial possible groups that you can generate, and you take, some combinations of those. I forget the exact numbers, how many these, but we balance the data. So like 50% of them, of these random matrices, will be simple and 50% of them will be non-simple. Can you use a neural network? We use a neural network here because we have two matrix features in your input. Can you distinguish the simple ones from non-simple ones? And again, it's this level of confidence that we get. So it really feels that, no matter how you represent these finite groups, the simple ones are in some sense different from the non-simple ones, with an underlying theorem that we don't know about yet. So this is nice, right? So this is we don't have to get, so this is kind of nice because we don't have to get 100%, because we're not after looking for a function that distinguishes the simple groups from the non-simple groups. What we're asking for is that could you conceive of a method of approach to this problem where simple groups and non-simple groups are distinguished without using, the standard Sylow theorems or Noether theorems? Because they're quite expensive, right? Because there is a way, if you compute the character table, you can do it, but computing character tables is not so easy. But this is literally, you're just plotting this and you're seeing that there's this separation. Why is there separation? I don't know. This is something, I've talked to many representation theorists about this, but it would be nice to approach this from this kind of ML inspired way. So that's an example. So you take other things like from combinatorics. So this one is another one, which I like, which I did a few years ago with Yao. So this is an interesting thing. So Yao, this is Yao Klabi Yao, and because he's Yao, he can do whatever he wants, in the sense that he can get unlimited funding. So Yao is one of the only people that I know who doesn't write grant proposals. He just calls up the premier and says, I need 1 billion next week. Is that okay? And the premier says, yes, fine. And so this is the reason I mention this is because so he got interested in this ML approach to math, and he did exactly this. He called up some government and some big head in the Ministry of Education. He says, I need, however, 10 to some number n, where n is not small, RMB. And he says, fine. And then this is done, and then it's done. So in 2021, a new institute in Beijing was formed called BIMSA. I should really put a logo for that, which is called the Beijing Institute for Mathematical Sciences and Their Applications, which is loosely affiliated with Tsinghua. And its mission is to do mathematics, physics, and machine learning in any of this combination, or data science in this combination. So one of the major themes of this institute is to do the machine learning explorations of mathematics, which is kind of nice. So here we have to, apply to EPSERC, and for, I don't know, 10 grand or something to do this. After 20 pages, and you're likely to get rejected. But Yao makes one phone call, and there it is, 1 billion done in 1 year, I think, or something. And the building's now completed. I think this is on 2023. I think this new campus was built up for this new institute, which is it's hiring a lot of people, so which is especially non-Chinese experts, which is kind of nice. So this is some exploration that we did, which is on, this is kind of interesting. I like this problem, which is, so we appealed to this one. Oh, by the way, to do this problem, we appealed to the GAP database. So that database has the first 10 million groups, I think, and then some sporadic. So we certainly didn't do all 10 million. It would be very nice if somebody, I mean, it's not big, but somebody really should take all 10 million and to see the separability of the simple from non-simple, for example, as a test. This one, we appeal to the Wolfram finite simple graphs database. It's something like 20,000 graphs. And then, of course, if you permute them, that can make it easily 1 million. And one thing that really was interesting was, we did some very simple things. Can you recognize, after seeing enough examples of acyclic graphs or planar graphs? But here's an interesting one, which is we tested whether a graph has Hamilton cycle versus whether it has Euler cycle by looking at it. Now, these two are vastly different problems, right? So the Hamilton cycle problem is the traveling salesman problem. Whether it goes through every vertex exactly once. The Euler cycle problem is a polynomial solution, a polynomial complexity solution that Euler's student even solved. This is the bridge of Königsberg problem that goes through each edge once. They're conceptually different because the Hamilton cycle problem is NP hard, but the Euler cycle problem is just polynomial. You can just easily solve it. And training it on a couple of 100,000 graphs, whether they exist, whether there exist Hamilton cycles or Euler cycles, because this database actually has that information. They gave pretty much around about the same level of performance. This got me thinking a little bit more. So whatever this measure of complexity, of machine learning complexity, it really has nothing to do with the computer science, the complexity. In some sense, you might expect it, because I think people have stochastically solved traveling salesman, in the sense that they won't give you an algorithm, but they will say 90% chance this graph has some. I think there are many papers in this area. There's like 90% chance there's some traveling salesman solution to this. So this is kind of interesting that by this kind of numbers, I mean I tried everything on your including your grandmother's kitchen sink, neural networks, support vector machines, and so on and so forth. So it's kind of interesting. I won't bore you with various other ones, but there's another one that I really liked, and then this is one that highlights the importance of feature, of the feature space representation, and this I learned from Tom Oliver, who is I think in the audience, and Qiuhuan Li. So number 3, of course, is hard, right? That was the problem that I gave him from the outset. For example, if you can recognize Liouville lambda, I think you can probably end up breaking banks, and then you won't see me anymore. Right? And so one of the very naive things that I did was to data scientists. That's interesting. So these two are they're card-carrying data scientists that know nothing about number theory, but they know a lot about machine learning, which is how much can we try to learn from this kind of stuff, playing around with the BSD conjecture, right? And there we got pretty much random, because the features that we put in for the elliptic curves were but the only one that I knew very well is the Weierstrass representation. You just give this or the Weierstrass Tate coefficients, but they can get very, very huge. And then if you try to extract things like rank of elliptic curves from that feature, it's impossible. It's as random as Sarnak's challenge. On the other hand, then I started talking to card-carrying number theorists like Tom and Qiuhuan, and they tell me, well, one shouldn't look at the Weierstrass coefficients. One should look at the L coefficients of the L function, the Euler coefficients of the elliptic of the L function of the elliptic curves. And there, if you try to do BSD, then you get much better behavior in terms of predicting rank and other features. Interestingly, there is a strong BSD conjecture. This is way out of my comfort zone, but at least I can try to state it in what I understand. So the BSD conjecture says that the analytic rank of your elliptic curve should equal to the order vanishing of your L function. So this is kind of unexpected connection between complex analysis and number theory, and that's why it's such an important conjecture. But there is a strong version of BSD which says that the order vanishing, the L function, you have L function constructed from the elliptic curve. Do I give an example? I'm just trying to say Oh no, so but we get this L function, and then you take the derivative evaluated at, I think, and you get the actual L dash over R factorial, and it's equal to some combination of seven quantities like Tamagawa and rank and other stuff. And apparently the most difficult quantity of these is the Tate-Chavaret-Rich group. So Tom can correct me if I'm saying wrong things. And that one, when you try to machine learn that from the Euler coefficients, did turn out to be the most difficult one to control. So there's a reason why that's hard. So this is kind of interesting. This complexity that we're venturing into is more like it's nothing to do with complexity in the PNP sense. Is probably nothing to do with the Kolmogorov sense, but this is a new sense of complexity in the sense how hard the problem is. As you know, this is in some way this is a good measure of how hard a problem is in mathematics. I know how likely is this problem going to be an open conjecture versus like somebody would like find a proof. And so in some sense, this is, I guess I'm trying to begin to quantify this idea of hardness. So that's where I'm going with these things. So I think I'm almost I'm so nearing the end. So this kind of exploration, this top-down exploration mathematics is clearly useful. So I mean, other than speeding up computation. So I'm going back to physics a little bit. Speeding up computation is great. So for example, this one, there was a really fun project that I did with Ashmore and Overwood, which was we took Donaldson's algorithm for computing numerical Clavier metrics, right? So this is an interesting problem. So there is no known analytic Clavier metric other than for elliptic curves. It's incredible. Yau's theorem was completely non-constructive. It just says that there exists a Ricci flat and it's unique within certain Chern class, but there's no known analytic result. So Donaldson came up with a very beautiful numerical way that he proved you can converge very fast to get this metric. So what we did was to just sample Donaldson's output and with a very simple feed-forward network. And that was able to speed up this algorithm by at least two orders of magnitude, which is kind of nice. Because when you're just doing numerical sampling of patches and claviers, this is great. So you can do it. And the people that have done more serious work, like Douglas and Anderson and friends, they actually Taylor constructed a neural network whose activation function is what they call a holomorphic polynomial activation function, which is not usually used in the ML community. And then this network has a loss function, which is, have a very clear loss function, which is, how close is your overall Ricci scalar when integrated close to zero, right? So you can optimize on that using this tail work, and that really has improved the Donaldson algorithm significantly. So this is very nice. So obviously this kind of work is very, very useful for what we do. But I'm now also very, very, very much interested in this idea. I think that's the thing that I was talking earlier with Yanis about, which is conjecture formulation. So with Kim, we have this possible, well, this is a proto-conjecture, is that there's some kind of separating hyperplane between simple non-Coopers in some representation. And it would be nice to prove this in some sense. These guys have come up with an exact formula for cohomology of surfaces by just mapping out the regions. But because when you compute like a bundle cohomology, say even like O of K comma M in a bigraded bigraded ring. So an algebraic variety represented as say in product of two projective space. So in this bigraded world, you can just your bundle cohomology, say O of K comma K comma M plotted in the lattice of Km will have regions that are 1, regions that are 0 that are separated by linear regions. So they were able to extract this and then predict that's what they should be, and then that you can actually prove that now. So that's done. Then there are various other ones. Oh, there's a really nice one that I'm actually currently, and again, this is done with Tom Oliver and Kyuhan Lee and Pozniakov and Andrew Sutherland, which is, we call it memorations. I think my only contribution to this project is to say, well, this looks like memorations, because these are card carrying number theorists. So it's kind of an interesting feature where you plot certain averages over conductor range in whatever range you take, and you see a quite unexpected oscillation in this space. So I think you can ask Tom more about this, which is, I mean, to me it looks very beautiful, but apparently to these number theorists, that's actually a new feature that has been missed completely before, and that was detected from initially by doing these machine learning experiments. So I should advertise that, but then I will. So basically, I'm suggesting that you invite Tom Oliver to give a talk on this, because he's very excited by this memoration. He's so excited, it got me excited. This is not my world, but apparently it's a very nice feature. This is called memorations of elliptic curves and L functions. And to go back to this, another one that I mentioned earlier. So this is a great triumph that was last year, which is this DeepMind, Oxford and Sydney collaboration on Nature, which was essentially what they did was to plot knot volumes against all possible features. So stuff like crossings and other stuff. But now, of course, if you plot it, you're not going to get anything because it's too high dimension to visualize. So instead of plotting, they did saliency analysis. So they did a feature analysis on what are possible salient features on which the volume of knots could depend on. And they extracted the one that they could. And I don't remember which one it ultimately came to. And then once they extracted those two key features, they did a regression on these. And then they got 100% robust result. And then it's a new known, it's a new and previously unknown exact formula of the volumes of knot depending on two of the salient on two of the salient features. And I think the regression even turned out to be linear, so which is perfect. And then they went ahead and proved it. So that's why this collaboration got a lot of attention, because that's exactly what I've been saying, that this machine learning for the mathematics community today is what the intuition of Gauss should have been for the 19th century. And I think we are now slowly entering this era where we can really use this to help us formulate interesting interesting conjectures, which then you can prove. And of course, for numerical analysis, you don't need to do anything. So here's a quick thing that gives you a quick metric, then great. You don't need to, you can play with it. So this hardness that I keep on measuring to, that I don't have a good definition for, I'm trying to plot it at least. It is very difficult to find a numerical problem in which your machine learning algorithm will not do better, even your generic one. And analytic number theory, as I said, is the most difficult one, in the sense that you're not going to find some patterns in primes just by staring at it or using any ML approach. Oh yeah, and I think yes, and there's a new journal, and I highly encourage people to I think I was one of the co-editors on this, I think, where this kind of machine learning exploration in pure mathematics and mathematical physics is it's very hard to find a good journal. Experimental mathematics they don't really like this kind of stuff. So submit to this. That should be fun. And I think that I'm right on the spot, so I think I'll stop here. Thank you very much.